Hi, grade 10s. So you've officially made it to my favorite lesson, probably of the year, most certainly within the unit. The reason I like these kind of problems is that the question, it gives us the answer, and really you have all the tools. It's all about manipulation, and it's all about algebra. This has always been something that I like. I like to be able to manipulate equations. So here's an example of what we're going to see today. It would say prove that cos of x times the tangent of x, all divided by sine x equals 1. Although this looks daunting, and you're like, oh my goodness, what is happening? There are a few different things that we can do. Do you like that little panda? That's you saying, oh no. A few different things that we can use to make it more appropriate or make it more bearable. The first thing we want to do is we want to look to see what type of identities, we're going to learn what a few of these are, can help us to solve these equations. So we always want to make our identities and change them and write them only in terms of sine and cosine. So in that question above, I'd want to get rid of that tangent. The second thing I look to do is I always look to factor. Factor helps me to reduce my fractions. If I have a fraction, or two different fractions, I want to look to make common denominators. And the very fourth thing that we're going to do is any other techniques, so maybe multiplying through by a coefficient or anything, to make sure that my final answer equals the value on the right. So in this example, equals 1. This really comes down to practice. The more that you do, the better that you get, because you start to see tricks and similarities. Now, for the different types of trig identities that you're going to see, I've boxed them here in blue. These are all different types of identities, and there are more. Okay, there are things called double angle identities, tons of different identities, but these are the ones that we're going to use. The first one that you are expected to know that you would not be given is the tangent identity, just in saying that tangent is the ratio between sine and cosine. Your reciprocal identities, we've seen these before. This is just how we wrote cosecant. So remember, cosecant was 1 over sine theta. Secant was 1 over cosine. And you'll notice that I've written cotangent differently. Generally, we say cotangent is 1 over the tangent of theta. But if I want to simplify in terms of sine and cos, the reciprocal would be cosine over sine. The identities here in orange that you see are ones that we would give you that you would just need to learn how to manipulate. And we're going to do this through practice. The pink one here, I've put it in pink because this is something that we're going to use so often that hopefully it does become part of your repertoire, but in certain situations it will be provided. So the first thing we're going to do is try an example. Using the example above, prove that cosine times tangent over sine x equals 1. This is where you get to pick the most complex side of the equation. And in doing so, you only manipulate this side. So we're only manipulating one side. It doesn't matter which one you choose. Choose the more complex. If I looked on the left and I looked on the right, definitely the left-hand side is more complex. So the first thing that I want to do is get my tangent in terms of sine and cosine. So cosine of x multiplied, but instead of tangent, remember we recall our first identity, that tangent is sine. I was going to write sine theta, but sine x over the cosine of x, all divided by the sine of x. We keep the right-hand side equal to 1. You will notice, woo, math magic, it cancels. Cos over cos cancels. I'm left with sine of x over the sine of x equals 1. And you can see a little bit more math magic. Cancel, cancel. I'm left with 1 equals 1. You didn't have to show that step, but you're more than welcome to. Once I get to this point, this is where we end our proof. Remember, using Q, E, D, or a small square. Congratulations, you have just done your first identity, and honestly, they're addicting. These proofs, you're going to learn to love them. There's also a funny comic if you want to take a moment to read it, and if not, go to example 2. Prove that cos of x equals secant x minus sine x tan x. I look to see which side is more complex, and I'm going to see that the right-hand side of the equation is more complex. This is what I'm going to work with. On the left-hand side, we leave it as cos of x, and what I'm going to do right now is I'm just going to rewrite out the equation just so that I have it here. First step, we want to get our tangents, everything in terms of sine and cosine. So I leave the left-hand side. I recall that secant of x is 1 over cos of x, minus sine of x is fine, and tangent, recall, is sine of x all over the cos of x. I simplify the right-hand side in my second term by multiplying this term through. I'm left with sine of x all squared. Notice there are 2 of those terms all over the cos of x. Okay, sine x times sine x is sine of x all squared. Here I have 2 different terms. I'm going to keep my left-hand side the same, and you will see that I already have a common denominator. This becomes 1 minus sine squared x, just using my different format, over cos of x. It's at this point when you see this section on the top that you should have like alarm bells going off in your head. That's my version of a bell. It doesn't really look like a bell, but it is. It looks like a ghost. This is part of my identity. This is one of my Pythag identities. Sine squared x plus cos squared x equals 1. If I were to manipulate this equation and isolate for cos squared x, I'm left with 1 subtract sine squared x. This is the term that I have up top. So where I see that 1 minus sine squared x, I'll replace with cos squared x. Cos squared x all over the cos of x. Recall that cos squared on the top is a cos times a cos, so I get cancellation that's happening. I'm left with the cos of x. Left-hand side equals right-hand side. Q, E, D. Question 3. Prove that the sine of sine squared x over 1 minus cos of x equals 1 plus cos x. Okay, so on the left-hand side, or I look to see which one is more complicated. For me, that one looks way more complex. So that's the side that I'm going to choose to manipulate. Sine squared x, there's not much I can do here, other than recalling that this is part of my identity. From above, if I were to isolate, sine squared x is 1 minus cos squared x. This is something that you start to see with practice in terms of simplifying. Now I'm also going to be really nice and just show you the funniest thing that's happening right now. So you can enjoy. This is my, oh, where is she? Hi, kitty cat. Okay. And you can see, so that's her. She's joining our little conversation. I cut her head out. But just so you know, that's my little cat. Her name is Mariah. So seeing this with practice, sorry for the little delay, on the top of my expression, instead of writing sine squared theta, I'm going to write 1 minus cos squared x all over 1 minus the cos of x equals the right-hand side. On the top, if you recall and you think hard enough about this, this is really a difference of squares. On the top, I have 1 plus the cos of x, and I have 1 minus the cos of x. You can see this cancellation that's going to happen with my denominator. That wonderful math magic. And I'm left with my final expression, 1 plus the cos of x equals 1 plus the cosine of x. I have proved my identity, and I'm good to go. Addictive, I told you, kind of fun. We're starting to progress on the difficulty, which just means I need to look harder and harder to reduce my functions. Question 4, and this is our last one. Prove that that whole mess on the left-hand side equals 2 tan x over the cosine of x. So this is the side that I'm going to work with, the more complex side. The very first thing that I see is I have two different functions, and these functions don't have common denominators. So I want to fix that by multiplying the first term by 1 plus sine of x, and my second term by 1 minus the sine of x. What that allows me to do is it allows me to give them the same common denominator of 1 minus sine x and 1 plus the sine of x. My second term, same denominator, 1 plus sine of x, and we keep our right-hand side the same. You do not have to show that in one step. I generally show it in 2 steps, I generally show it in 1. So I would go right from the first line, the first part of the equation, generally to this step here. I'm going to keep my brackets for now, just to simplify. And I have one denominator, 1 minus sine of x, 1 plus sine of x. Keeping everything the same on the right. This is where you need to be careful. That negative is going to change these signs, and it's going to change the way your question comes out. So being very careful in that, I'm left with a minus 1 and a plus sine of x all over 1 minus sine x, 1 plus sine of x. And I have a little bit of cancellation. Negative 1, positive 1. On the top, I'm left with 2 sine of x all over this denominator. Okay. At this point, if you haven't looked to expand that denominator, one of the reasons I would go about doing that is because that is a perfect difference of squares. This is going to come out to cancel really nicely. So when I expand this, recalling that I need to FOIL, on the top, I'm left with 2 sine of x. And on the denominator, 1 times 1 is 1. I have plus sine x and then a negative sine x. That will cancel. I'll show that here, but you do not need to. And then the last term would be minus sine squared x. Okay, this is where the magic is going to happen. This is my favorite part of the identity. My signs cancel. Okay? I'm left with 2 sine x all over 1 minus sine squared x. Okay, everything on the right stays the same. Again, alarm bells. Why? See, it's another bell. Woo. Because this on the bottom should look similar. This is our identity. Remember, cos squared x. Okay, this becomes sine x all over cos squared x. And remember, I'm always looking up to the top. Does it match the right-hand side yet? Does it match the right-hand side? 2 tan x over cos of x. 2 tan x over cos of x. So it doesn't match yet, so I'm not done. With practice, that should say sign, not sim, you will see that by splitting up the denominator, although you're like, Miss Palmer, what's the point of that? Cos of x. We all know that's technically true, right? I can multiply cos times cos to give me cos squared, but this just lets me see that, oh, look, I have a sine over a cosine. Recall that a sine over a cosine is tangent. And finally, my left-hand side equals my right-hand side. And I am done. I'm going back through here, filling out my right-hand side of the equation. That's up to you. You can also use that formatting with those arrows if you need to. But those are our trig identities. So hopefully I've sparked a little bit of interest in you for your assigned problems. Checking out your textbook, page 273. I encourage you to work with pairs just to talk it through and look for those manipulations. Try one out, but really, in terms of these, you need to be comfortable with the struggle. So give yourself time to play around with all those questions. Okay, so working. Is that working? Is it not? What else can I do to make it match the right-hand side? Thanks for listening, and I hope you enjoy a wonderful upcoming break. Thank you.